What causes water droplets to bounce when they hit a surface? What determines whether a surface is hydrophobic or hydrophilic? And what does it mean when a surface is superhydrophobic? It all comes down to surface tension. Surface tension, or surface energy, is a tensile or contractile force. It's given in units of newtons per meter, which is force per unit length, or joules per meter squared, which is energy per unit area. Surface tension kind of acts like a stretched elastic membrane, kind of like a balloon. Because surface tension is a contractile force, each section of the balloon is pulling on each other, resisting changes in shape. What causes surface tension? It's caused by the attractive or cohesive forces between water molecules. If we look at a pool of liquid, the molecules that are inside the pool are experiencing cohesive forces with neighboring molecules. They are completely surrounded by other molecules and are enjoying their interactions. The interactions lower the energy state of these molecules. These are happy molecules. But molecules on the surface of the pool are only surrounded by half the number of other molecules, so they only experience half the amount of cohesive interactions. These are unhappy molecules. They are at a higher energy state than molecules inside the pool. To minimize the number of unhappy molecules, liquids adjust their shape to expose the smallest possible surface area. That's why water droplets are spherical, and why in space, blobs of water also take the form of spheres. But what about water droplets resting on a surface? What determines whether they will bead up and roll off or spread out completely? When a water droplet contacts a surface, it takes the shape of a spherical cap. Before, we learned that all liquids have surface energy. Actually, every single surface has surface energy. A surface can be thought of as the interface between two phases. Before, when we were talking about the surface tension of a liquid, we were talking about the surface energy between a liquid and air. There's also the surface energy between solid and air, and the surface energy between liquid and solid. If we call this angle the equilibrium contact angle, we can do a force balance on the line of contact with the surface. We want to balance the forces in the x direction. We have the surface energy between solid and vapor, the surface energy between solid and liquid in the opposite direction, and the x component of the surface energy between liquid and vapor. Rearranging gives this, which is Young's relation. Young's relation shows that the contact angle that a droplet makes with the surface is related to all of these surface energies. If the equilibrium contact angle is greater than 90 degrees, the surface is hydrophobic. On the other hand, if the contact angle is less than 90 degrees, the surface is hydrophilic. If the contact angle is greater than 150 degrees, the surface is defined as being superhydrophobic. Water droplets that touch superhydrophobic surfaces will ball up. If the contact angle is less than 5 degrees, the surface is defined as being superhydrophilic. Water droplets that touch superhydrophilic surfaces will spread out completely. This is useful for anti-fog coatings. If the surface is superhydrophilic, then any water that contacts the surface will form a thin film instead of forming droplets on the surface. So what makes a surface superhydrophobic or superhydrophilic? There are two main factors, and the first is surface chemistry. The surface chemistry determines whether the surface has low or high surface energy, which then determines whether the surface is hydrophobic or hydrophilic. Generally speaking, surfaces with low surface energies are hydrophobic, and surfaces with high energies are hydrophilic. Things such as Teflon and other plastics have low energy, while things such as metals have high energies. The second factor is surface roughness. In general, surface roughness will make a hydrophobic surface even more hydrophobic, and a hydrophilic surface even more hydrophilic. Scientists have been trying to determine what kind of tiny structures make surfaces superhydrophobic or superhydrophilic. They've been looking at examples in nature, such as the lotus leaf, to obtain these special properties. There are two different states that a water droplet can be in when it contacts a rough surface. To go over these two different models, we will call theta E the equilibrium contact angle, which is the contact angle for an ideal flat surface. We'll call theta star the apparent contact angle, which is the contact angle on a rough surface. These two models were developed by Wenzel and by Cassie and Baxter, and they show how surface roughness can affect a water droplet's contact angle. The first state that a water droplet can be in when it contacts the surface is a Wenzel state. In this state, there are no air bubbles underneath the droplet, and the droplet is in complete contact with the surface. The droplet actually sticks very well to the surface, and it's called a pinned droplet. In the Wenzel model, The surface roughness is quantified by R, which is the real surface area divided by the projected surface area. Since every surface has some sort of roughness, because no surface is completely smooth at the molecular level, we can assume that R is greater than 1. The Wenzel model states that cosine theta star is equal to R times cosine theta E. Since R is greater than 1, the cosine of theta star is greater than the cosine of theta E. This is a very important statement. Let's look at what happens when theta E is less than 90 degrees. If theta E is 45 degrees and R is 1.2, we can calculate the value of theta star. Theta star turns out to be 32 degrees. So when theta E is less than 90 degrees, we can see that theta star is less than theta E. Now let's look at what happens when theta E is greater than 90 degrees. If we set the value of theta E to 135 degrees and R equal to 1.2, we can calculate that theta star is equal to 148 degrees. Now we can see that theta star is greater than theta E. So when the surface is hydrophilic, theta star is smaller than theta E. When the surface is hydrophobic, theta star is bigger than theta E. This equation shows that roughness will make a hydrophobic surface even more hydrophobic and hydrophilic surfaces even more hydrophilic. If a droplet is in the Cassie-Baxter state, the water droplet actually sits on top of tiny air bubbles. In this state, water droplets will bounce or roll off. This is useful for water repellent and self-cleaning surfaces. A surface can be self-cleaning because any water droplets that contact it will roll off, picking up any dirt along the way. Generally speaking, the Cassie-Baxter state occurs for very, very rough surfaces. A special form of the Cassie-Baxter model shows that theta star is dependent on the percent of solid that is in contact with the droplet. As this value approaches 0, or in other words, if the droplet is sitting mostly on air pockets, the cosine of theta star approaches -1, and theta star approaches 180 degrees. So, to summarize, how a water droplet behaves when it contacts a solid is dependent on surface energies. The contact angle describes whether the surface is hydrophobic or hydrophilic. Surface roughness can also cause surfaces to become superhydrophobic or superhydrophilic, as shown by the Wenzel or Cassie-Baxter model. A cool example of how hydrophobicity can be useful is how the Namib desert beetle collects water to drink. This beetle lives in the Namib Desert in Africa. The beetle has a very special back where there are little hydrophilic islands that are surrounded by hydrophobic areas. Tiny fog droplets can collect on the hydrophilic islands and grow to larger droplets. Once the droplets are large enough, the droplets roll down the beetle's back and is collected to drink.